the choice of the learning rate alpha will have a huge impact on the efficiency of your implementation of gradient descent. And if alpha, the learning rate, is chosen poorly, gradient descent may not even work at all. In this video, let's take a deeper look at the learning rate. This will also help you choose better learning rates for your implementations of gradient descent. So here again is the gradient descent rule. W is updated to be W minus the learning rate alpha times the derivative term. To learn more about what the learning rate alpha is doing, let's see what could happen if the learning rate alpha is either too small or if it is too large. For the case where the learning rate is too small, here's a graph where the horizontal axis is W and the vertical axis is the cost J. And here's a graph of the function J of W. Let's start gradient descent at this point here. If the learning rate is too small, then what happens is that you multiply your derivative term by some really small number. So you're going to be multiplying by a number alpha that's really small, like 0.0000001. And so you end up taking a very small baby step like that. Then from this point, you're going to take another, tiny little baby step. But because the learning rate is so small, the second step is also just minuscule. The outcome of this process is that you do end up decreasing the cost J, but incredibly slowly. So here's another step, and another step, another tiny step, until you finally approach the minimum. But as you may notice, you're going to need a lot of steps to get to the minimum. So to summarize, if the learning rate is too small, then gradient descent will work, but it will be slow. It will take a very long time because it's going to take these tiny baby steps, and it's going to need a lot of steps before it gets anywhere close to the minimum. Now, let's look at a different case. What happens if the learning rate is too large? Here's another graph of the cost function. And let's say we start gradient descent with W at this value here. So it's actually already pretty close to the minimum. So the derivative points to the right, but if the learning rate is too large, then you update W via a giant step to be all the way over here, and that's this point here on the function J. So you move from this point on the left all the way to this point on the right, and now the cost has actually gotten worse. It has increased because it has started out at this value here, and after one step, it actually increased to this value here. Now, the derivative at this new point says to decrease W. But when the learning rate is too big, then you may take a huge step going from here all the way out here. So now you've gotten to this point here. And again, if the learning rate is too big, then you take another huge step at the next iteration and way overshoot the minimum again. So now you're at this point on the right, and one more time, you do another update and end up all the way here. And so you're now at this point here. So as you may notice, you're actually getting further and further away from the minimum. So if the learning rate is too large, then gradient descent may overshoot and may never reach the minimum. And another way to say that is that gradient descent may fail to converge and may even diverge. So here's another question you may be wondering. What if your parameter W is already at this point here, so that your cost J is already at a local minimum? What do you think one step of gradient descent will do if you've already reached a minimum? So this is a tricky one. When I was first learning this stuff, it actually took me a long time to figure it out. But let's work through this together. Let's suppose you have some cost function J, and the one you see here isn't a square error cost function. And this cost function has two local minima corresponding to the two valleys that you see here. Now, let's suppose that after some number of steps of gradient descent, your parameter w is over here, say equal to 5. And so this is the current value of w. This means that you're at this point on the cost function j, and that happens to be a local minimum. Turns out, if you draw a tangent to the function at this point, the slope of this line is 0, and thus, the derivative term here is equal to 0 for the current value of w, and so your gradient descent update becomes w is updated to w minus the learning rate times 0, where here, that's because the derivative term is equal to 0. And this is the same as saying, let's set w to be equal to w. So, this means that if you're already at a local minimum, gradient descent leaves w unchanged because it just updates the new value of w to be the exact same old value of w. So concretely, let's say if the current value of w is 5 and alpha is 0.1, after one iteration, you update w as w minus alpha times 0, and it is still equal to 5. So if your parameters have already brought you to a local minimum, then further gradient descent steps do absolutely nothing. It doesn't change the parameters, which is what you want, because it keeps the solution at that local minimum. This also explains why gradient descent can reach a local minimum even with a fixed learning rate alpha. Here's what I mean. To illustrate this, let's look at another example. Here's the cost function j of w that we want to minimize. Let's initialize gradient descent up here at this point. If we take one update step, maybe it'll take us to that point. And because this derivative is pretty large, gradient descent takes a relatively big step, right? Now, we're at this second point, where we take another step. And you may notice that the slope is not as steep as it was at the first point, so the derivative isn't as large, and so the next update step will not be as large as that first step. Now, we're at this third point here, and the derivative is smaller than it was at the previous step, and we'll take an even smaller step. As we approach the minimum, the derivative gets closer and closer to 0, so as we run gradient descent, eventually we're taking very small steps until you finally reach a local minimum. So just to recap, as we get nearer a local minimum, gradient descent will automatically take smaller steps. And that's because as we approach the local minimum, the derivative automatically gets smaller, and that means the update steps also automatically get smaller, even if the learning rate alpha is kept at some fixed value. So that's the gradient descent algorithm. You can use it to try to minimize any cost function j, not just the mean squared error cost function that we're using for linear regression. In the next video, we're going to take the function j and set that back to be exactly the linear regression model's cost function, the mean squared error cost function that we had come up with earlier. And putting together gradient descent with this cost function, that will give you your first learning algorithm, the linear regression algorithm. So previously, you took a look at the linear regression model, and then the cost function, and then the gradient descent algorithm. In this video, we're going to put it all together and use the squared error cost function for the linear regression model with gradient descent. This will allow us to train the linear regression model to fit a straight line to our training data. Let's get to it. Here's the linear regression model, and to the right is the squared error cost function, and below is the gradient descent algorithm. It turns out if you calculate these derivatives, these are the terms you would get. The derivative with respect to w is this 1 over m, sum from I equals 1 through m, then the error term, that is the difference between the predicted and the actual values times the input feature xi, and the derivative with respect to b is this formula over here, which looks the same as the equation above except that it doesn't have that xi term at the end. And if you use these formulas to compute these two derivatives and implement gradient descent this way, it will work. Now, you may be wondering, where did I get these formulas from? They're derived using calculus. If you want to see the full derivation, I'll quickly run through the derivation on the next slide. But if you don't remember or aren't interested in the calculus, don't worry about it. You can skip the materials on the next slide entirely and still be able to implement gradient descent and finish this class, and everything will work just fine. So in this slide, which is one of the most mathematical slides of the entire specialization, and again is completely optional, we'll show you how to calculate the derivative terms. Let's start with the first term, the derivative of the cost function j with respect to w. We'll start by plugging in the definition of the cost function j, so j of wb is this. So 1 over 2m times this sum of the squared error terms. And now remember also that f of wb of xi is equal to this term over here, which is wxi plus b. And so what we would like to do is compute the derivative, also called the partial derivative, with respect to w of this equation right here on the right. If you've taken a calculus class before, and again, it's totally fine if you haven't, you may know that by the rules of calculus, the derivative is equal to this term over here, which is why the 2 here and the 2 here cancel out, leaving us with this equation that you saw on the previous slide. So this, by the way, is why we had defined the cost function with the 1/2 earlier this week, is because it makes the partial derivative neater. It cancels out the 2 that appears from computing the derivative. For the other derivative with respect to b, this is quite similar. I can write it out like this, and once again plug in the definition of f of xi, giving this equation. And by the rules of calculus, this is equal to this, where there's no xi anymore at the end. And so the 2's cancel once more, and you end up with this expression for the derivative with respect to b. And so now you have these 2 expressions for the derivatives, and you can plug them into the gradient descent algorithm. So here's the gradient descent algorithm for linear regression. You repeatedly carry out these updates to w and b until convergence. Remember that this f of x is a linear regression model, so it's equal to w times x plus b. This expression here is the derivative of the cost function with respect to w, and this expression is the derivative of the cost function with respect to b. And just as a reminder, you want to update w and b simultaneously on each step. Now, let's get familiar with how gradient descent works. One issue we saw with gradient descent is that it can lead to a local minimum instead of a global minimum, where the global minimum means the point that has the lowest possible value for the cost function j out of all possible points. You may recall this surface plot that looks like an outdoor park with a few hills with the grass and the birds is a relaxing outdoor hill. This function has more than one local minimum. Remember, depending on where you initialize the parameters w and b, you can end up at different local minima. You can end up here, or you can end up here. But it turns out when you're using a squared error cost function with linear regression, the cost function does not and will never have multiple local minima. It has a single global minimum because of this bow shape. The technical term for this is that this cost function is a convex function. Informally, a convex function is a bowl-shaped function, and it cannot have any local minima other than the single global minimum. So, when you implement gradient descent on a convex function, one nice property is that so long as your learning rate is chosen appropriately, it will always converge to the global minimum. Congratulations! You now know how to implement gradient descent for linear regression. We have just one last video for this week. In that video, we'll see this algorithm in action. Let's go to that last video. Let's see what happens when you run gradient descent for linear regression. Let's go see the algorithm in action. Here's a plot of the model and data on the upper left, and a contour plot of the cost function on the upper right. And at the bottom is the surface plot of the same cost function. Often W and B will both be initialized to 0, but for this demonstration, let's initialize W to be equal to negative 0.1 and B to be 900. So this corresponds to f of x equals negative 0.1x plus 900. Now, if we take one step using gradient descent, we end up going from this point of the cost function out here to this point, just down and to the right. And notice that the straight line fit is also changed a bit. Let's take another step. The cost function has now moved to this third point, and again, the function f of x has also changed a bit. As you take more of these steps, the cost is decreasing at each update. So the parameters w and b are following this trajectory. And if you look on the left, you get this corresponding straight line fit that, fits the data better and better until we've reached the global minimum. The global minimum corresponds to this straight line fit, which is a relatively good fit to the data. I mean, isn't that cool? And so that's gradient descent. And we're going to use this to fit a model to the housing data. And you can now use this f of x model to predict the price of your client's house or anyone else's house. For instance, if your friend's house size is 1,250 square feet, you can now read off the value and predict that maybe they could get, $250,000 for the house. To be more precise, this gradient descent process is called batch gradient descent. The term batch gradient descent refers to the fact that on every step of gradient descent, we're looking at all of the training examples instead of just a subset of the training data. So in computing gradient descent, when computing derivatives, we're computing the sum from I equals 1 to m. And batch gradient descent is looking at the entire batch of training examples at each update. I know that batch gradient descent may not be the most intuitive name, but this is what people in the machine learning community call it. If you've heard of the newsletter The Batch that's published by DeepLearning.AI, the newsletter The Batch was also named for this concept in machine learning. And then it turns out that there are other versions of gradient descent that do not look at the entire training set, but instead looks at smaller subsets of the training data at each update step. But we'll use batch gradient descent for linear regression. So that's it for linear regression. Congratulations on getting through your first machine learning model. I hope you go and celebrate, or maybe take a nap in your hammock. In the optional lab that follows this video, you see a review of the gradient descent algorithm as well as how to implement it in code. You also see a plot that shows how the cost decreases as you continue training more iterations. And you also see a contour plot, seeing how the cost gets closer to the global minimum as gradient descent finds better and better values for the parameters w and b. So remember that to do the optional lab, You just need to read and run this code. You won't need to write any code yourself. And I hope you take a few moments to do that and also become familiar with the gradient descent code, because this will help you to implement this and similar algorithms in the future yourself. Thanks for sticking with me through the end of this last video for the first week, and congratulations for making it all the way here. You're on your way to becoming a machine learning person. In addition to the optional labs, if you haven't done so yet, I hope you also check out the practice quizzes, which are a nice way that you can double check your own understanding of the concepts. It's also totally fine if you don't get them all right the first time. And you can also take the quizzes multiple times until you get the score that you want. You now know how to implement linear regression with one variable. And that brings us to the close of this week. Next week, we'll learn to make linear regression much more powerful. Instead of one feature like size of a house, you learn how to get it to work with lots of features. You also learn how to get it to fit nonlinear curves. These improvements will make the algorithm much more useful and valuable. Lastly, we'll also go over some practical tips that will really help for getting linear regression to work on practical applications. I'm really happy to have you here with me in this class, and I look forward to seeing you next week.